Hello guys, my name is IBM. I am based in Ulaanbaatar, and again I'm recording the October-November 2024 papers as required as asked by some of my students. Today I'm going to record 9702 paper 22. Do not forget to visit our website which we are developing, that is www.cieresourcemaster.com, where we upload or where we shall be uploading most of the resources. You can also find the past papers there for your respective categories. Just note that the website is still developing, but the physics resources are there, and I'm one of the members of the physics department, and therefore by visiting the website you will have supported our website to grow. So today I want to go to paper 2 AS level structured questions, paper 2 October November 2024. And straight away I'll just go to the first question. I'll skip the data which we are using to. Question number 1, state what is meant by a vector quantity. Remember, a vector quantity is a quantity which is denoted by both magnitude and direction. So this one is a quantity which denotes or which has both magnitude that is size and direction. A quantity which denotes both magnitude and direction, that is a vector quantity. It has both magnitude and direction. For a scalar quantity, it has only magnitude. A sphere falls vertically through a liquid. It is falling, so it is going downwards. The density of the liquid is 830 kilograms per meters cubed. The sphere has a radius of r and a constant velocity v. The velocity is constant, which means the acceleration is 0. The drag force D, of course, the drag force is like friction, and friction occurs when there is relative motion. Since motion is downwards, we can predict that the drag force D must be upwards on the sphere because it tends to oppose the motion. The drag force acting on the sphere is given by this equation, where nu is a property of the liquid. The time the SI base units of nu. So one, we shall begin by making nu the subject. So nu is going to be equal to D divided by 6 pi r times V. Then we shall list all the units of the corresponding quantities. For example, the SI base units of, let's say D to start with. D is a force, and force is kilogram meters per second squared. So this is going to be kilogram meters per second squared. Then the SI base units of R, that is radius, that will be meters, and V, that is speed, which is meters per second per second. So it means that the SI base units of nu is going to be those of D, which is kilogram meters per second squared, divided by of course we ignore 6 pi, radius is meters, times V, which is meters per second. So this is the same as, of course, 1m cancels with that, so it becomes kilograms. Of course, s power minus 2 divided by s power minus 1, this will be s power minus 1. We subtract the powers. Then we have m at the denominator, so it will be m power minus 1 and then s power minus 1. So the answer is going to be kilograms per meter per second. Then state the equation showing the relationship between the magnitudes of W, D and upthrust. Of course, upthrust is an upward force, so the upthrust is always upwards. Then D was the drag force, which depends on the direction of motion. Since the sphere is falling downwards, the drag force, which is like friction, is going to be upwards. So upthrust, because the speed is constant, the resultant force must be zero, which means the upthrust plus the drag force must be equal to the weight. The upthrust plus the drag force must be equal to the weight. So the upthrust plus the drag force is equal to the weight. The volume of the sphere is 4.6 centimeters cubed. The drag force is 0.32 newtons. Calculate the weight of the sphere. So of course we know that upthrust is equal to the weight displaced. The weight of the fluid displaced. And this is going to be equal to m times g, where m will be equal to the density times the volume of the liquid, then times g. So it means the upthrust is going to be equal to the density of the liquid, which was 830, I think. Density is 830 times g, which is 9.81, then times the volume, which is 4.6 times 10 to the power, because this is power minus power centimeters cubed is the same as 10 to the power of minus 6 to change it to meters cubed. So this is times 10 to the power of minus 6. So this is going to be our upthrust. I'll check this with my calculator. 830 times 9.81 times 4.6 exponent minus 6. So this is 0.037 newtons. So that is the upthrust. But we mentioned that the upthrust plus D equals to the weight. So the weight is the upthrust plus the drag force. The weight is going to be 0.037 plus the drag force, which is 0.32. And I think when we sum up this, we shall have 0.357 or approximately 0.36. So I'll just write here 0.36 newtons. Question number 2, define momentum. Of course, we know that momentum is mass times velocity. So momentum is the product of mass and velocity. So I'll just simply write here mass multiplied by the velocity. That's momentum. A child stands on a scooter on a horizontal ground. The combined mass of the child and the scooter is 16 kilograms. The child starts from rest and pushes once on the ground with her feet, which causes her to accelerate. The push lasts for a time of 1.1 seconds. The speed of the child and the scooter after the push is 0.6 meters per second. Determine the average resultant force acting horizontally on the child and the scooter during the push. So initial velocities acting horizontally on the child and the scooter during the push. So it starts from rest, so initial velocity is 0. That means the resultant force on the child is equal to the rate of change of the momentum, which is the same as mass times the change in the speed divided by delta t. So the mass of the child, the combined mass is 16. Then the velocity changes from 0 to 0.6. So I'll just say 0.60 minus 0. That is the change in the speed. Divided by the time it takes for that change. That is 1.1. From my calculator, 16 times 0.6 divided by 1.1. So that is 8.72 recurring. I mean 7272, so I'll just write 8.7. Later, the child in B travels down a slope at a constant angle to the horizontal as shown in the figure. At point A, her speed is 0.6. So here speed is 0.6. She has a constant acceleration, so acceleration is constant. So if the acceleration is uniform, then the equations of motion can work. Equations such as S equals to ut plus a half at squared would be employed. V equals to u plus at would be employed. V squared equals to u squared plus 2as, because the acceleration is constant. Constant acceleration means the equations of motion or the Subert equations can be employed here. After a time of 3.7 seconds, she reaches point B. So between A and B, the time is 3.7. Calculate the distance x traveled by the child along the slope from A to B. Okay, so I think I can use so many methods. Let me start with the first one. Using S equals to ut plus a half at squared. S is going to be x. Initial velocity was 0.6 at A. Then the time is 3.7 plus a half. The acceleration is constant, 0.85. Then times t, which is 3.7 squared. So x equals to, so I'm going to have 0.6 times 3.7 plus 0.5, that is a half, times 0.85 times 3.7 squared. So this is giving us 8.04 or 8.0. That's method number one. Let me try method number two. Method number two, I may first find the speed at B. The speed at B is going to be the speed at A plus the acceleration times the time between A and B. So this is going to be 0.60 plus 0.85 times 3.7. I'll check the calculator again. So 0.6 plus 0.85 times 3.7. That is 3.75. Let me just write 3.75 meters per second. That is the speed at B. So if I want to use this speed to find x, then there are two ways of doing this. I can use S equals, there's another formula where S equals to a half into u plus v, that is the average speed times time. If the acceleration is constant, the displacement can be the average speed times time if the acceleration is constant. So I can say x equals to a half into initial velocity 0.6 plus the final velocity, which is 3.75, then times t, which is 3.7. So I have 0.6 plus 3.75 divided by 2 times 3.7. The answer is still the same, 8.0 meters. I can also check method 3. This is method 2. Method 3, I'm going to use the v squared equals u squared plus 2as, where I will say that now when I make s the subject, s is x, so I'll say x equals to v squared minus u squared divided by 2a. V squared is 3.75 squared minus 0.60 squared divided by 2 times 0.85. Let me check this one. So 3.75 squared minus 0.6 squared divided by 2 times 0.85. So it is the same. To two significant figures, it is 8 point. Actually, this one is giving me 8.1. 8.1. Approximate, or 8.06 meters. It's almost the same. The only difference comes in the last digit because of rounding off. If I had not rounded off V to 3.75, this could give me a value which doesn't round off this to 8.1. So in a nutshell, I'll just take V as approximately 8.0. The examiner would determine the tolerance, but I'm very sure this is correct. At B, the child in C applies the brakes with a constant force to maintain a constant velocity, that is zero acceleration. The work done by the braking force between B and C is 250 joules. Work done is 250 joules. Determine the magnitude of the braking force. So of course, we know that the work done equals to the force times the displacement in the direction of the force. So the force is going to be the work done, which is 250, divided by the displacement. I think point C was at 18 meters, so this is going to be divided by 18. So 250 divided by 18, that is 13.8 recurring, 13.88 recurring, which is going to be approximately 14. So the force is going to be 14 newtons. On the figure 2.3, sketch the variation of the kinetic energy of the child and the scooter with the distance traveled from point A to point C. Numerical values for kinetic energy are not required. Note that from A to B, the speed was constant. The speed from A to B, the speed increased from 0.6 to 3.75. So the kinetic energy increased. Because the speed increases uniformly, since the acceleration is constant, A is constant from A to B, so V increases uniformly. V increases uniformly. If V increases uniformly, then the kinetic energy is also going to increase uniformly. So this is going to be a straight line. But it will not be zero because initial kinetic energy is not zero, because the initial velocity is not zero. So initial kinetic energy is not zero because initial velocity is not zero, it is 0.6. So I'm going to draw a line which does not start from zero, but the kinetic energy increases. Then between B and C, B to C, the speed remains constant as mentioned, which means kinetic energy is going to remain constant. Kinetic energy will remain constant because V is remaining constant. Therefore, between for the next 18 meters, I will draw just a horizontal line. Okay. So that will be our graph. The variation of stress with the strain for a metal P is shown in the figure. Point E is the elastic limit of the metal. E is the elastic limit. Use the figure to determine the Young modulus for P. So of course we know that Young modulus equals to the stress divided by the strain, which is the same as the gradient. So I'll just take the most clear point. For example, I can take this point here. So on the x-axis, this is 1, 2, 3, 4, 5. So this is 0.75, and on the y-axis, this is, I think this is 18. So the Young modulus is going to be the stress over the strain, or the gradient. So that will be 18 times 10 to the power of 7 divided by on the x-axis we have 0.75. It is percent. So this one is going to be 0.75 divided by 100, which is 0.0075. So this is 0.0075. So I'll just press my calculator. 18 exponent 7 divided by 0.0075. So this is giving me 2.4 times 10 to the power of 10. So that is 2.4 times 10 to the power of 10. You could also use 0.5, and I think that is 12. You could use that also. So it means Young modulus in that case would be 12 times 10 to the power of 7 divided by 0.005, I think. You have to change this from a percentage to be 0.005. I think the answer is the same, 2.4 times 10 to the power of 10. Then on the line in the figure, draw a cross to show the limit of proportionality. The limit of proportionality is where the straight line stops. And by eyesight, I think the straight line stops here. So I put an X here. And I'm going to label this Q. So it is stopping here. The limit of proportionality is where the straight line stops. That's where stress stops being directly proportional to strain. Then state the conditions necessary for an object to be in equilibrium. Of course, we know that number one, the resultant moment, you can call it torque, about any point is 0. That's number one. Number two, resultant force. In any direction is also 0. So there is no resultant force, there is no resultant moment. The wire is used to hold a uniform shelf, be horizontally in equilibrium. The wire is connected to the midpoint of the shelf, which means this distance is 0.65. When I divide it by 2, 0.65 divided by 2. So this distance here is going to be 0.325 meters. That is that distance there, which also means this distance here, okay, the distance from here up to where this one is, that distance is going to be 0.65 minus 0.12. The distance is 0.53 meters. I need to rub something here. This distance is 0.53 meters. Now the rod was uniform, its weight is at the midpoint, and they put and the wire is also at that midpoint, so there is a weight here for the rod. The length of the shaft is 0.65 and its weight is 33, so 33 is acting at that same position and its distance is still 0.325. A cup of weight 1.5 newtons, so the weight of the cup is also there, which is 1.5 newtons, with its center of gravity at a horizontal distance of 0.12 meters from B. By taking moments about A, determine the tension in the wire. So I will just simply say the sum of clockwise moments should be equal to the sum of anti-clockwise moments. The sum of clockwise moments equals the sum of anti-clockwise moments. For clockwise moments, we have 33 newtons, 1.5. So that would be 33 times the perpendicular distance. Of course, we know that moment equals to the force times the perpendicular distance. Perpendicular distance from the pivot. Perpendicular distance from the pivot. That is where we are taking the moments from. That is the pivot. So that is 33 times the perpendicular distance, which is 0.325 plus 1.5 times the perpendicular distance, which is 0.53, should be equal to. So for the anticlockwise moments, I'm going to resolve. Let me change the color. I'm going to resolve the tension. Of course, there is tension here. When I resolve the tension, it will point upwards. Resolving tension in the vertical, it will be T sine of 50. So T sine 50 is now acting at a perpendicular distance of 0.325. Therefore, that will be causing the anticlockwise moment. So this is going to be T sine of 50 times perpendicular distance, which is 0.325. Okay, so I'm going to just simplify this. I'm just going to simplify this. So I will say that T is going to be equal to 33 times 0.325 plus 1.5 times 0.53 divided by 0.325 sine of 50. So from my calculator, 33 times 0.325 plus 1.5 times 0.53. Then, so that is 11.52 divided by, we have 0.325 sine of 50. That is 0.249. So we can divide 11.52 divided by 0.249. So that is 46.27 or approximately 46 newtons. The stress in the wire is 1.5 times 10 to the power of 7 pascals. Determine the radius of the wire. So we know that stress is equal to force over area. This is the same as the force divided by pi r squared, that is the cross-sectional area, which means that the area, the radius is going to be equal to F over stress times pi under the square root. Then I'll just substitute. So this will be the square root of 46, which was the tension, divided by this pi times 1.5 times 10 to the power of 7. So pi times 1.5 exponent 7, 46 divided by the answer, square root of the answer. So that is 9.9 times 10 to the power of minus 4, or 9.88 times 10 to the power of minus 4 meters, or I will just say 9.9 times 10 to the power of minus 4 meters. More items are added to the shelf, doubling the stress. So the stress is going to be 3 times 10 to the power of 7 pascals. The wire is made of the metal, P from A. P from A. In A, what do we have? Okay. The wire is made of metal P from A. Now the stress is 3, which is still much smaller. Okay. The stress is 3, it has been doubled, but it's just 3 times 10 to the power of 7. Use the figure to state and explain whether the wire will behave plastically or elastically as the stress doubles. Of course, it will still behave elastically, because even though the stress has doubled, it is still less than the elastic limit. It has not yet reached the elastic limit. So we shall say the new stress is still less than the stress at the elastic limit. The new stress is still less than the stress at the elastic limit, and the new strain is also going to be less, of course. And because remember, if the Young modulus is a constant, then the stress is directly proportional to strain. So it means, and the new strain is less than the strain at elastic limit. At elastic limit. So the wire still behaves elastically. So the wire still behaves elastically. If the stress had gone beyond the elastic limit, then the wire would behave plastically, but because the stress is still less than the stress at the elastic limit, then the wire can still continue to behave elastically as before. With reference to the direction of transfer of energy, compare the oscillations of transverse and long waves, progressive. So for longitudinal, we know that the particles, or the wave oscillations of particles is perpendicular to the direction of transfer of energy. For longitudinal, we know that oscillations are parallel to the direction of transfer of energy. So I will say transverse Sorry about this. So transverse, what's the spelling of transverse? Transverse waves have oscillations of particles perpendicular to the direction of transfer of energy. Then longitudinal waves have oscillations of particles parallel to the direction of transfer of energy. Okay. Then a pipe is open at one end and closed at the other. So it is a closed pipe in a nutshell. The piston can slide freely and is at a distance of 4.5 times 10 to the power of minus 2 meters from the open end of the pipe. The loudspeaker is positioned near the open end of the pipe and emits a sound wave of a single constant frequency. A stationary wave is formed in the pipe as illustrated in the figure. On the figure, draw a letter A at the position of an antinode. Of course, the antinode is at the open end, so I'll put A here. Of course, at the closed end, we have a node, so A should be near the open end. Then the speed of sound in A is 340. Determine the frequency. So we know that the general wave equation V equals to lambda F. And of course, the wavelength, we know that for the fundamental mode, this is a quarter of a cycle. It is something like this. We have just taken a quarter. This is a quarter of a cycle that has been shown there. So it is a quarter of a wavelength. The length given is a quarter of a wavelength, so that means the wavelength is going to be 4 times L, where L, this is L. So the wavelength is going to be equal to 4 times the length, which is 4.5 times 10 to the power of minus 2. So it means the frequency F is going to be equal to V, which is 340, divided by wavelength, which is 4 times 4.5 times 10 to the power of minus 2. I'll check my calculator. 340 divided by 4 times 4.5 exponent minus 2. So that is 1888.8, which is approximately 1900. So the frequency is approximately 1900 hertz. The piston is moved to the left. The piston is moved to the left. The frequency of the sound wave emitted by the loudspeaker is then changed so that a stationary wave is formed with the same number of antinodes. There's only one antinode. If the number of antinodes remains the same, also the number of nodes remains the same. So it means the length L has increased but that is the distance between the node and the antnode has increased, but the frequency has not changed. The length has increased, which means the wavelength has increased, so the frequency is supposed to decrease because the frequency is going to be inversely proportional to the wavelength. Since the speed of sound is going to remain the same, it is still in air, so the speed of sound is going to remain the same. So from lambda equals to 4L, the length has increased, or the distance between a node and an antnode has increased. If the distance has increased, the wavelength has increased. Since the speed remains the same for sound in air, then it means the frequency must be lower. So I will simply say that the node antnode distance is now longer, so the wavelength of the wave is longer, and since the speed of sound remains constant, since speed of sound remains constant, then the frequency of the wave is lower. So the frequency will decrease. Okay, I think that is enough for waves. Define electric potential difference. V is equal to, I think it is E over Q, the energy transferred from electrical to other forms per unit charge. Energy transferred per unit charge from electrical to other forms. So when a charge passes through a component in a circuit, the electrical energy of the charge is converted to other forms such as heat, light, and so on and so forth. So the energy transferred per unit charge from electrical to other forms such as heat. Power supply, 3 resistors and a component X are connected in the circuit shown in the figure. Okay, it is almost the same as the one we saw in paper 2-1. Identify component X. Of course, that one is a heater. You must have seen that right from IGCSE. That is the symbol for a heater. Show that the PD across the resistor of resistance 0.86 is 6 volts. Okay, so we have the current and we have the EMF. So we can find we have the current which is going through this. I can find the PD directly. So the PD is going to be I times R, which is going to be the current, which is given as 7.0 times R, which is 0.86. So that PD is going to be 7 times 0.86 that is 6.02, which is approximately 6.0 volts. Determine the current I1. Determine the current I1. So we can find the PD across. We can find the PD across the parallel combination, which is the same as the PD across 170. So I'll say PD across the parallel combination. PD across the parallel combination, or PD across 170 ohms, is going to be just the difference. The EMF was 230 minus the PD across the resistor, which is in series the power supply, which was 6 volts. So that is 224 volts. So the PD across these 2 points is 224 volts. So it means I can now say the current I2 is going to be, of course, V over R, which is going to be 224 divided by R, which is 170. I2 is going to be 224 divided by 170. That's 1.32. So that means I1 is going to be just the difference, because total current, the current entering the junction was 7. The current entering here is 7. The current going here is 1.32. So the I1 is just the difference. So I1 is going to be 7.0 minus 1.32, which is 7 minus 1.32. That is 5.68 amperes, or you can write 5.7, but me I'll write 5.68. Of course, there could be another method to find that, but I think that one is the easiest. That is the easiest. Then calculate the PD across component X. PD across component X. Now we know the total PD across the 2.4 ohm resistor and X, which is 224. If we can find the PD across, okay, we now know the current I2. Do we know the resistance X? We can still find the resistance X and use that. But I will start with the simplest method, where I will find the PD across. PD across 2.4 ohms and X. We have already seen that this is 224 volts. And the PD across 2.4 ohms alone is going to be, of course, we know the current I1 times 2.4, which is I1, we got I1 as 5.68. I1 is 5.68 times 2.4. So that PD is going to be 5.68 times 2.4. That is about 13.63 volts. So it means the PD across X alone is going to be 224 minus 13.63. 224 minus 13.63, that is 210. So this is going to be 210. So the answer here is going to be 210. That could be method number 1. Let me try method number 2, maybe with a different color. So I can first find resistance of X. So resistance of X is going to be Of course, resistance of X plus 2.4 is going to be the PD across X over total resistance. So, okay, resistance of X plus 2.4 is going to be the PD across both, which is 224 divided by the current entering, which is 5.68. The current entering into the parallel combination. So which means resistance of X is going to be 224 divided by 5.68 minus 2.4. Let me try to subtract this. 224 divided by 5.68 minus 2.4. That is 30, is it 37? That is, okay, approximately 37. So this is approximately 37 ohms. That is resistance of X. Then if I want to find PD of X, of course I will still use I times R, where I was I1, that is 5.68. Then R is Rx, which is 37. So we have 37 times 5.68, which is approximately 210. Okay, so whatever method you use. Then capture the power dissipated in component X. So of course power has several methods. We can use power is equal to IV. That would be the current was 5.68 in X. Then V we have seen is 210. So the power would be 5.68 times 210, approximately 1192, which is 1200. 1200 watts. That's method number one. Method number two, I can use power equals to I squared times R. I is 5.68 squared times resistance of X, we got it as 37. So that is times 37. 5.68 squared times 37, which is approximately the same, 1200 watts. I could also use power equals to V squared over R, which is 210 squared over resistance of X. Resistance of X we got as 37. 210 divided by 37, sorry, it is 210 squared divided by 37. It's almost the same, 1200. So the power is going to be 1200 watts. The purpose of the circuit is to provide the power to component X. Determine the percentage efficiency of the circuit. So this is the power, which is because the purpose is to provide power to component X, and yet the power dissipated in X is 1200. We can find the power which is total input power, because we know that efficiency, percentage efficiency, is going to be equal to the useful power output divided by the total power input times 100 to make it a percentage. Then power input total power input is going to be, of course, that is I times V. Total current was 7.0 amperes. Then V is going to be the EMF. Total power input is going to be I times E, where E is the EMF. The EMF was, I think, 230. Yes. So it means the efficiency Percentage efficiency is going to be 1200 divided by 7 times 230 times 100 to change it to percentage. So 1200 divided by 7 times 230 times 100. That is approximately 75%. The resistor of resistance 170 ohms is removed, leaving an open circuit. So the lower resistance is removed, leaving an open circuit. That means the only resistance we have is X, which was 37, and then we have 2.4. So the total resistance has reduced, has increased, because the resistance in parallel reduces total resistance. Now total resistance has increased, which means the total current must decrease. State whether the current in the power supply increases, decreases, or remains the same. Of course, the current here, we have seen that total resistance, R total resistance increases. And we know that current equals to the EMF divided by total resistance, that is total current in the battery. If total resistance has increased, the current must have decreased. So we just say current decreases. And then we go to the last question. Compare an alpha particle with a beta particle. Compare an alpha particle with a beta particle in terms of masses and charge. We know that an alpha particle is a helium nucleus, which is He42. The mass is 4U, the charge is 2E, positive. Then beta, the beta is an electron, beta plus. So the mass is 1 over 18, 40U, and then the charge is just plus E. Okay. So we can simply say that the mass of alpha particle is much greater. This emphasis is very important. Is much greater than beta plus. Because the mass of alpha is 4U, the mass of beta plus is approximately 1 over 1840U. So the mass of alpha particle is much greater than the mass of a beta particle. Number 2, I think both particles are positively charged. But when we compare the magnitude of the charge, we notice that for alpha, it is twice for beta. So I will simply say magnitude the magnitude of charge on alpha particle is twice the charge on beta plus particle. Nucleus P undergoes alpha decay. So P is undergoing alpha decay to form Q. So P is giving us Q. Nucleus Q undergoes a further decay to form R. So Q is going to give us R. The proton number and nucleon numbers of P and R are shown on the figure. So starting with the P, nucleon number is 216, Proton number is 84. Then it is giving us an alpha particle, so this is plus alpha, which is 4, 2. So here the nuclear number will be 2, 1, 2, and the proton number will be 82. So Q must be here. Proton number 82, nuclear number is 212, so Q must be there. So in the figure, draw a cross to show the proton number and nuclear number of Q. Label your cross Q, so I have labeled here Q. State the names of the particles emitted as Q decays to form R. So when Q is 212, 82, decays to form R, and R, when we look at R, this is 83, the other one is 212, so this is 212, 83. This must be a beta particle, but is beta minus 0, negative 1 to balance the proton number. When a beta minus particle is emitted, this is accompanied by an antineutrino. When an electron is emitted, it is emitted by an antineutrino. So the particles, the name of the particles emitted, we have the beta minus, or you can just call it the electron, and we have the electron antineutrino. The electron antineutrino. Let me write the spelling of the word neutrino very well. Before the alpha decay, P is traveling at a constant velocity. After the decay, Q has a velocity of 1.3 times 10 to the power of 5 meters per second at an angle of 68 degrees to the original path of P. The alpha particle has a velocity of 150 times 10 to the power of 5 meters per second at an angle of theta to the original path of P as shown in the diagram. So first of all, I will resolve this in the vertical. Here this will be 150 times 10 to the power of 5. When I resolve with respect to the theta, that will be sine theta upwards. Then I resolve for Q downwards, and this will also be 1.3 times 10 to the power of 5 sine of 68. Since there was no initial motion in the horizontal, we shall only, it means initial momentum in the horizontal is 0. Use the principle of conservation of momentum to determine theta. So I'm going to just consider vertical momentum. Considering vertical momentum, so it means total momentum before in the vertical was 0 because the P was moving horizontally. Then after we have for the alpha particle, the mass of an alpha particle is 4u. The mass of P, I think P was, the nuclear number was 216, so the mass of this is 216 times u. Q, the nuclear number was 212, so its mass is 212 times u. So this is going to be alpha, which is going to be 4 times u, that is the mass, times the speed, which is 150, times 10 to the power of 5 sine of theta minus, because the alpha is upwards, the other one is downwards. Downwards we have 212 u times 1.3 times 10 to the power of 5 sine of 68. So u cancels, I think, and therefore sine theta is going to be equal to 212 times u times 1.3 times 10 to the power of 5 sine of 68 divided by 4 times u times 150 times 10 to the power of 5. So the power of 5 has cancelled. I'll just check with my calculator here. The power of 5 has cancelled. I'll just say 212. U has cancelled. 212 times 1.3 sine of 68 divided by 4 times 150. So sine theta is 0.426. 0.426. Then theta is going to be the sine inverse. Shift sine of the answer 25. So theta is going to be 25 degrees. Then calculate the kinetic energy of the alpha particle. Of course, we know that kinetic energy is a scalar quantity, so we don't even consider resolved values. A half mv squared. So this is going to be a half times the mass, which is 4u, so that is 4 times 1.66 times 10 to the power of minus 27. To change it to kilograms, this is the mass. When I change it to kilograms, because 1u is 1.66 times 10 to the power of minus 27 in kilograms. Then we multiply this by v squared, which is 150 times 10 to the power of 5, and this is squared. So we have where should I start from? Okay, 0.5, that is a half, times 4 times 1.66 exponent minus 27, then times 150 exponent 5, but this is squared. So that is 7.5 times 10 to the power of minus 13. 7.47 times 10 to the power of minus 13 joules, which is approximately 7.5 times 10 to the power of minus 13. I think that marks the end of this paper. Do not hesitate to visit our website to download papers from our website. Like I said, the resources are still being added by the different departments. With the time, it will be full, but I know most of the resources of physics are available. Until next time, I remain IBM. Bye-bye.